So thank you, everybody, for coming. Oh, please. So today we have Harry Arnold coming to talk to us. So Harry Arnold graduated in 21 from the University of Maryland, where he studied non-thermal electron energization and macro scale magnetic reconnection. I'd like you to say that 5 times fast. Afterwards, he did a postdoc at APL, where he became staff in 23. And during his time at APL, he's been studying magnetotail current sheet dynamics in both kinetic and global simulations. And today he'll be talking to us about his work on kinetic thin current sheets.
Thank you.
Thank you.
Yes, so my title here is Overstretched Thin Current Sheets and the Onset of Magnetotail Reconnection, Bridging Kinetic and MHD Models, which was an ambitious goal, and I think maybe the bridging the kinetic and MHD models didn't quite pan out the way that I had hoped to just yet, but I'll talk a little bit about it anyhow. You can also see that I forgot to change the location and date. Oh, my bad. Actually, before we move on, I do just want to point out this figure here. So this is from the Spicer 65 paper. These are Spicer orbiting protons and electrons. And basically, if you have a parabolic magnetic field like you might find in the magnetotail, your ions will gyrate around the field line until they reach the current sheet, and then some of them, the Spicer ions, can then turn into these meandering motion along the current sheet. And I just point that out because I'm going to be talking more about the importance of Spicer ions in these overstretched thin current sheets. So we're going to talk about some observations of the OTCS, overstretched thin current sheet. I'm going to talk about data mining based reconstructions, which might seem a little tangential, but the fact that they include these thin current sheets in the reconstructions, I think, makes a pretty compelling case for their existence. Then I'll discuss the new model that I've been working on with my co-author here, Misha Sitnov, which requires some anisotropy and it has agyrotropy in the current sheets. I'll talk about the force balance, and that's where the Spicer ions become super important. And then I'll move on to forcing these current sheets and also trying to make some sort of instability with the so-called BZ humps. And the short of it is that these thin current sheets appear to be a little bit more stable than the traditional Harris current sheets, which is a bit of a puzzle, but we can talk about that later. And then finally, I'll talk about my future directions, and that's where I start trying to talk about these thin current sheets in the context of global simulations, and we'll get there shortly. So this is just a brief, this is my one slide on substorms, just so we can all sort of think about them the way that I like to think about them. Basically, you have the solar wind, which is plasma from the sun with electromagnetic fields that hits the day side of the Earth's magnetosphere. You get reconnection, the field lines get swept back with the solar wind and apply pressure on the night side of the Earth's magnetosphere, stretching it out into its magnetotail, where eventually you get night side reconnection, earthward flows, dipolarization, and particle energization. So this is a great video from Wilferger et al. 2015 illustrating this. This is a simulation, and it shows you both the meridional plane, where you can nicely see the field lines, you get day side reconnection, night side reconnection, but then you can also see the equatorial plane, which I'm going to talk a lot about, because this is where you get those, you can see those flows, those purple lines, and you can see the dipolarization of the magnetotail. I'm going to skip the second video because I think we probably don't need it. So let's talk about observations. So here, this is from Runov et al. 2005. These are observations of current sheet thickness in the tail, basically measured because the magnetotail current sheet flaps up and down across the satellite, and you can measure its thickness. These are histogram normalizing the thickness to the ion Larmor radius, and what you see is a significant chunk of them are less than 10 ion Larmor radius, and there's even a significant fraction that's much smaller than that. So you have these very thin current sheets in the tail, and they're quite common. This is from a different paper. This is Rogers et al. 2024, much more recent. Here they were looking at time that MMS spent in thin current sheets in the XY or equatorial plane. And you can see that there does seem to be a slight bias towards the dusk side, but it's pretty much everywhere in the tail. And each of these pink dots here are so-called ion diffusion regions, which is where you can either get an X line where reconnection happens, or an O line, which is the center of your plasmoid. And what's particularly interesting is that there seems to be good correlation between where you're getting reconnection and where you're seeing thin current sheets. So now we're going to transition, we're going to talk about data mining a little bit. So data mining is this reconstruction method has been used by Misha Sitnov and Grant Stevens to reconstruct the Earth's magnetic field at a given instant in time. What they do is they take their database of about 10 million magnetometer measurements from satellites, throughout the magnetosphere, and they put them in this 5-dimensional state space where each point is characterized by the SML index, which is the substorm geomagnetic index, its time derivative, the SMR index, which is the storm time index and its time derivative, and then the solar wind driving electric field, which is basically how much energy the solar wind is putting into the system. And then for a given instant in time that they're interested in, they take about the 30,000 closest points in this 5-dimensional state space, and they fit their magnetic field model to it, which is described here. And then they get magnetic fields at every point in the magnetosphere. So here's an example. This is the equatorial plane. Each gray dot here is a virtual satellite. It's a magnetometer measurement that they're using to fit their field, their magnetic field model. And that's showing BZ, which is this is in GSM now, so it's a normal magnetic field to this plane. And each of these contours are just contours of BZ. And one thing that you see is this contour of BZ equal to 0. The earthward side of this contour corresponds to an X line. The tailward side corresponds to an O line. And when you look at the 3D reconstruction here, you immediately see that obviously this is an X line and there's reconnection going on, and you're forming this plasmoid tailward of that X line. So this data mining reconstruction method does prove to be quite accurate. There's a list of something like 26 IDRs, ion diffusion regions, that MMS has identified. And for each of those 26 events, Misha and Grant Stevens reconstructed the Earth's magnetosphere, and they got very good agreement for 24 of the 26 events, matching up an IDR with either an X line or an O line in the reconstruction. So we have reason to believe that these reconstructions are actually fairly accurate. And one thing, before I move on, I just want to point out that in their reconstruction, they have basically a magnetic field from 2 different equatorial current sheets. They have a thicker current sheet and a thinner current sheet, and they're explicitly they're represented differently. So you can actually keep track of the magnetic field due to the thin current sheet and the current in the thin current sheet separately from the thicker current sheet that it's embedded in. So let's talk a little bit about these thin and thick current sheets. So there's a lot of plots on the left here, but I really just want to focus on, say, these 2 plots here. This plot, this is showing the thickness in, I think, RE of the thick current sheet in green and the thin current sheet in orangish. And what you'll notice is that the thick current sheet is something like a few RE, whereas the thin current sheet is a fraction of an RE, which is really about an ion inertial length. So this is truly an ion scale current sheet that they get in their reconstructions. And this thickness here, this is not set by them. This is what the data tells them the thickness is. Then this plot down here, this shows the integrated current in those 2 separate current sheets as a function of time. And what you see, is that in the growth phase of substorms, which are these pink shaded regions, in pretty much every case, the amount of current in your thin current sheet increases. And then at onset, it suddenly decays. So this is suggesting that the thin current sheet plays an important role in the growth phase and the onset of substorms. But I also want to point out here that what they often see is a BZ hump, which is basically if you take a profile of BZ along the tail, you often see prior to onset a hump, and the BZ, a local BZ maximum is somewhere in the tail. But then after onset, you get this dipolarization, this flux transfer from further out in the tail, closer in, which is what you would expect. And I'll talk more about this BZ hump in the future. Yeah, okay. So to continue with this, here's another event. These top plots here are the growth phase of the substorm, the bottom plots are the expansion phase. The left, again, you have BZ and contours of BZ. You can even see a little localized hump right here. And after the growth phase, you do get some X lines popping out, but you definitely get dipolarization closer to the Earth. When you look at the current sheet, you again see this huge buildup of their thin current sheet in the tail that pretty much dissipates after onset, which is consistent with the story I've been telling. And when you switch to the meridional plane, it tells the same story. You see a nice intense current sheet right here, and afterwards it dissipates and you get near dipolarization. Oh yes, and there are all of my handy notes. Here's another event that I'm going to show. This is showing the SML index. These are solar wind magnetic fields. These three plots here are prior to onset, and what you're seeing is the intensification of that thin current sheet, and after onset, it again dissipates. You can see the same sort of thing in the meridional plane, where this current sheet is getting significantly more intensified, and then you can clearly see the dipolarization afterwards. But what's interesting is when you look at BZ, and I'll note here that the axis here does in fact go up to 60 Earth radii because they're now using data from Artemis. So they get out to lunar orbit. And they see this BZ hump deep in the tail near 40 RE that just kind of sits there. Tailward of that, there does seem to be an X line, which is possibly what creates the hump. But at any rate, the hump just sits there until after onset, suddenly you get the flux redistribution and you get dipolarization near the Earth. So this is, the story here is really all about how the thin current sheets are important in the substorm growth phase and they dissipate after onset, and that BZ hump may be playing a role in the instability as well.
All right, are you going to comment at some point on the asymmetry that hump has in the Y direction?
No, I wasn't going to comment on that. Yeah, it's a fair point. I really couldn't say why the data mining reconstructions appear to be asymmetric. Maybe the only thing that I'll note is that often, especially in the growth phase, for whatever reason, and we can talk about this. Actually, this is interesting. I guess I really haven't thought about it, but you know, they often see X lines on the dusk side of the magnetotail. And I think that that's actually consistent with in situ observations. And I think Yisun Liu has done some PIC simulations showing that, let's see if I remember the argument exactly, but basically the X line spreading is such that the electrons are more frozen into the field, so they tend to drag BZ dawnward, which is their drift direction. And so you're more likely to get reconnection on the dusk. And that is at least consistent with substorms. I think if you start switching to storm time substorms, then the ring current can reverse the effect. But I never thought about that before, but I wonder if that's why they're seeing this bias of the BZ hump on the dusk side, because it's coming from this X line, which is on the dusk side.
Okay, thank you.
Very interesting question.
Harry, do you know what data gives the 40-ish RE? Is geotail maybe?
Right, so, and I should have tracked down this plot and I apologize I didn't, but there's this great figure showing the data density as a function of location in the equatorial plane. And basically you have pretty good coverage up to almost 30 RE, and then you have good coverage out around 60 RE, and there's really nothing in between. So this BZ hump, there's only a handful of points really in the in-between region. But I think that the BZ hump, I know Misha spent a lot of time trying to see if this is a reliable signature or if it's an artifact. And his conclusion, and he would be the one to ask more questions about this, but his conclusion is that it is likely to be true. Yes, and the only other thing that I'll say to that is that BZ humps have been observed in situ data, but going out to 40 RE is maybe not a lot of in situ data out there. Okay, so let's talk about the force balance of these thin current sheets. For isotropic MHD force balance, you can work out pretty easily that the length scale along the tail of the current sheet divided by the width of the current sheet should be about equal to the low magnetic field over the normal magnetic field in the current sheet. And that magnetic field ratio is about 20, which should give you, if your current sheet thickness is a DI, it should give you a length of about 2 RE, which would tell you that the current sheet length in the tail is only 2 RE, which is definitely wrong. We know that it goes out at least 10 times as far, if not more. So there's some issue with the isotropic force balance. It can't just be achieved with isotropic pressure. And in fact, Artemiev in 2016 tried to resolve this with electron anisotropies. And he comes up with this really nice plot showing the force balance along the tail. So the solid line here, this is J cross B divided by the isotropic pressure gradient. And you can see if MHD force balance was sufficient, then this line would be a constant at 1, and it is significantly larger than 1 as you go out in the tail. And when you take into account electron anisotropy, you arrive at this dashed black line, which is a little bit better, but it's still far from equilibrium. So electron anisotropies and isotropic plasma is not sufficient. And in fact, just to continue this, good, you would get the current densities of about 1 to 3 nanoampere per square meter in the tail. And here's a bunch of in situ data at different distances in the tail, 18, 25, 40, 60 RE, and all of these are significantly larger than just a couple nanoamperes per square meter. So the takeaway here is that you need something more besides isotropic plasma and electron anisotropy. And so obviously we're going to talk about ion anisotropy. So if you look at the force balance and you're just trying to balance your J cross B force with the divergence of the pressure terms, this is the equation that you arrive at. For gyrotropic plasma, you can fairly straightforwardly write down this off-diagonal pressure component. This is the ion pressure XZ as this dependence on the parallel and perpendicular pressures. So it's gyrotropic but anisotropic. So if you have anisotropy, you might be able to contribute to this term in your force balance, right? So we've already determined that these terms over here are insufficient, but maybe with ion anisotropy, we can do that. And it turns out, Yushkov et al. 21 has these 20-odd plots from different events showing the ion and electron anisotropy as a function of the thinning. So the x-axis here, this is BZ, and the thinning process goes from the right side to the left side of these plots. And what you'll notice is that in almost all of these, at the left side, there is some weak anisotropy in the ions, something a little bit larger than 1. So we have this weak anisotropy. Maybe we can do some approximation based on that. So we're going to do this approximate 1D overstretched thin current sheet equations, which we're going to use in our PIG simulations. And our 3 small parameters are the anisotropy, the embedding, which is basically the thickness of your thin current sheet to the much thicker embedded current sheet, and your stretching parameter, which is always small in magnetotail simulations, and it's just your normal magnetic field compared to the low magnetic field. And we're also going to take advantage of this quasi-adiabatic invariant, which is approximately conserved for Spicer ions, because we suspect that Spicer ions are playing a big role here. And so you can write down a bunch of equations, and it looks gross, and we're not going to talk about this in great detail, but there's a paper if you're interested. But the bottom line here is that if you just look at the terms in the red box here, which is what you get when there is no anisotropy, where it's isotropic, you recover the Harris equilibrium. And so what we're plotting here are several different quantities, and for each one, this dotted or dashed black line is your isotropic Harris equilibrium, and then the colors refer to different amounts of anisotropy. And so you can see that there is some significant difference as you go to larger anisotropy in the magnetic field. The density is largely unchanged, but importantly, the current takes on this 2-scale structure where you have this thin current sheet embedded in a thicker current sheet. The electric potential is also very, very tiny, even for larger anisotropies. This is times 10, so it's extremely small and therefore negligible. And these are your anisotropies. So we take that approximate equilibrium, and something else that I do just want to briefly point out here if you study these equations, what you'll notice is that the distribution function is symmetric. So at t equals 0, at the beginning of our simulations, there is no off-diagonal pressure. It's not isotropic, but there's no off-diagonal pressure in the beginning. And so here are our the results of our simulations. This is after 60 ion cyclotron times when we've reached equilibrium. And let's look at a couple points here. So this is our current, and you can see that our current sheet is much thinner than the thicker density plasma sheet. You have isotropy right at the very center of the current sheet, but upstream of that, you recover your anisotropic ions. It is agyrotropic inside the current sheet. And finally, at the end, you have this off-diagonal ion pressure term, which is what we're saying is crucial for your force balance. And finally, I just want to compare a thin current sheet, which is its top plot, to its Harris isotropic current sheet, where we tried to match the thickness of this Harris sheet to the thickness of the thin current sheet at the left boundary. And what you see is that the thin current sheet, the current sheet is much more extended in the x direction than the Harris current sheet, which is also one of our goals here. So looking at the force balance of this current sheet, here I'm plotting a number of terms in the momentum equation at t equals 0, and then again at t equals 60, which is the end of our simulation. The solid black line here, this is J cross B. That's the force that we're trying to balance with the pressure. And then the red lines are for the ions, the blue lines are for the electrons, and the dashed and dash dotted are sort of these sums. In particular, the dash dotted black line, this is J cross B minus the sum of the divergence of the pressures, which, if you're in equilibrium, that should be 0. You immediately see that at the beginning of our simulation, it is non-zero, which is what we expect because we only have an approximate equilibrium at the beginning. But by the end of our simulation, it's effectively 0. And what's happened is you can see that the solid red line appears to be largely unchanged. The blue lines are largely unchanged. The black line is largely unchanged. The only thing that changes is dashed red line, and that's that off-diagonal pressure. So what gives us the force balance in OTCS is the off-diagonal pressure. And finally, this bottom plot here, this shows the averaged quantity of that dash dot black line, which again should be 0 if you're in force balance. So we average it between -20 and -60, plotted as a function of time. And on top of that, we just have this exponential decay with a decay rate of 10 ion cyclotron times to show that we do achieve force balance by the end of the simulation, and it appears that this current sheet reaches equilibrium in about 10 ion cyclotron times. So finally, I take these two cuts here. This is at two different values of x. This is at the left boundary, and this is at the center of the box. And I plot the plasma density and the plasma current density at the beginning and end of the simulation. And so the red and blue lines here are the plasma density, and green and black are current. And you can see that beginning and end throughout the box, the density and the current density are really not changing substantially at all. Which is good because that tells us that our approximate equilibrium is pretty solid. But what's interesting is that you have this thin current sheet embedded in the plasma sheet, as I said before, and the current sheet appears to be basically the upstream magnetic field of that current sheet is about 1/2 of B naught. So when you work through the force balance, and I'm not going to go through this in detail, this is all done in the paper that we have. But basically, this off-diagonal pressure component is responsible for about 1/3 of the J cross B force. The rest of the J cross B force is balanced with the isotropic pressure and the electrons. So let's talk about the particles now. Which particles are actually responsible for this off-diagonal pressure component? So this plot here, the top left, this shows the distribution of ions integrated over the outer plane direction, By. And it looks pretty much like a Maxwellian, to be honest, because again, we just have weak anisotropy. This distribution is taken in this red box here, so you can see it's a little bit upstream of the current sheet, kind of right where we have a significant amount of off-diagonal pressure. And then I have all these green circles, which you can see fairly well, that represent different annuli, because the next thing that I do is I measured the amount of density in each one of those circles as a function of that radial velocity. So as you go out, where's the density? So this peak here, this corresponds to your thermal ions. Then the bottom left plot here, this is showing the final distribution minus the initial distribution, and then I multiply it by Bx Bz. And what I'm doing here is I'm trying to see in the phase space where you're getting this contribution to the off-diagonal pressure. And so you can see the red areas, that's where it's positive, and the blue areas where it's negative. And it turns out that this ring I'm showing, this is corresponds to the peak in off-diagonal pressure. And so this plot here, very similar to the density, but now it's for this off-diagonal pressure. And you can see that this is where we're peaking, which is in fact super thermal. This is about twice the thermal speed that's giving us our off-diagonal pressure. And when I start a bunch of test particles right at this star, and I evolve them in the equilibrium magnetic field, they look like this. There are basically two different kinds. One looks like those meandering Spicer ions that I showed at the beginning, but the other one are these so-called figure-of-8 Spicer ions. And spoiler, it's the figure-of-8 that are the most important here. Yes, and then okay. So now what I've done is I've recreated the density and off-diagonal pressure plots, but now instead of just integrating over all of By, I split the distribution function into these four regions. So this is distribution as a function of By. And we basically have a left standard deviation and then a left tail, and similar for the right-hand side. So when you look at the densities, as you expect, it's very symmetric, left and right, not a lot of difference. But when you look at the off-diagonal pressure component, it's all coming from which one? The left standard deviation, which is these guys right here. And it turns out that these guys are your figure-of-8 ions, and the right ones, the right-going ones, are your meandering ions. So basically what happens is our equilibrium, where we do explicitly take into account Spicer ions with our quasi-adiabatic invariant, we assume Bz equals 0. So we're basically picturing our ions like this. But of course, Bz is not 0. It gives you this curved field, and that effectively tilts your figure-of-8 orbits, which then produces this off-diagonal ion pressure, giving you force balance. So that's our thin current sheet equilibrium. But the next thing that we're interested in here is reconnection with this current sheet. You know, we want to know, how do we get this current sheet to be unstable? So I just want to talk about a couple things here. You know, MHD, or this isotropic Harris current sheet. Well, MHD has no kinetic physics, obviously Harris can, but MHD has no kinetic physics, and as a result, you often get reconnection in these global MHD models much too close to the Earth, something like 12 RE, you know, less than 15 RE for sure. These are two different MHD simulations, actually two different MHD models that both produce very close X-lines. But all these statistics show, and the plots that I showed at the beginning all show, that X-lines are typically happening around 20 RE in the tail, certainly more than 15 RE. So there's an issue here. And when you do these isotropic Harris current sheets in PIC models, you see something kind of similar. So this is one PIC simulation where they're driving with an electric field at the top and bottom boundaries, and they get reconnection here at about 15 DI, which DI is about, what is it? 15 DI corresponds to about 1.5 Earth radii. So if you were to say that the left-hand side of this box is like the night-side transition region, say 10 RE or so, then this is telling you that reconnection happens at 11 or 12 RE, which again is way wrong. This bottom plot here, this is no forcing. This is just the BZ hump instability. So if you have a BZ hump in the tail that's unstable to ion tearing, your hump moves earthward. You can actually see it here. Here's your BZ hump. It moves earthward. The amplitude increases, and in its wake, you get reconnection. But again, your reconnection is happening at 15 DI, much too close to the Earth. So our you know, what we are trying to show is that in thin current sheets, you're going to get something more realistic. So let's compare thin current sheets to the Harris isotropic current sheet. So one thing to point out is that our simulation box is much larger now. We're 120 DI, whereas before it was like 30 or 60. Otherwise, these are very similar simulations. We match the thickness at the left boundary, and then it's just thin current sheet versus Harris. So when we force it, the X line forms much later, about twice as long in the thin current sheet than it does in just your Harris current sheet. And it's also a little bit more tailward, although interestingly, both these cases, it happens at around 80 DI, which is like 8 RE. So that would correspond to about 18 RE in the tail, which is more realistic, even for the Harris case, which was a bit of a surprise. But the other thing to point out here is that prior to reconnection, both these simulations, you form this watershed region. Basically, there's a divergence in the flow prior to reconnection. Then reconnection takes over, and then you get this significant great divergence in the flow with your reconnection outflows. And you can actually see that a little bit better in this 2D image here. This is showing the ion watersheds, the electron watersheds. But this is basically suggesting, since it's happening on this larger scale or ion scale effect, that this is ion tearing prior to reconnection. So in the Harris case, you still get this watershed, but eventually you do get reconnection, and then you can even see multiple X lines suggesting electron tearing. In the thin current sheet case, you end up with just a single X line. So maybe you do get a little bit of electron tearing there, but all in all, this thin current sheet appears to be more stable than the Harris current sheet. Let's go to the next page. Okay. So now if we put a hump in the thin current sheet, so now we're comparing a BZ hump in the thin current sheet with no forcing and with weak forcing. I mean, if you recall, for Harris, even without forcing, you do end up with reconnection. But now in the thin current sheet, without forcing, your BZ hump just moves earthward. The amplitude never increases. You never see watersheds. You never see reconnection. That's it. It just moves earthward. With a little bit of weak forcing, it moves earthward. Maybe you see some amplitude increase. This could potentially be a boundary effect, but it looks promising. But for sure, you do see reconnection and you do see watersheds. So that's all consistent. Once you force it, then you can get reconnection. But otherwise, we still have this picture where thin current sheets are potentially more stable than their Harris counterparts. And part of this might be because for thin current sheets, what sets the thickness of that current sheet is that ion Larmor radius, which is the size of your figure 8 orbit. But for a Harris current sheet, the thickness is arbitrary. You set it to whatever you want. And in fact, in those earlier Harris simulations where with the BZ hump instability, the current sheet was under 2 ion Larmor radii, which is basically where your thin current sheet is set. So that could be playing a part of the role in the stability. Then I just want to put this plot here. This is showing our driving electric field that we apply in these simulations as a function of X. And the reason why I put that there is this thinking about the thickness. Basically, I thought, okay, well, what if instead of forcing across the whole box, what if we just force in front of the BZ hump and try and thin the current sheet in front of it? Would that get you an instability? So that's what I did. This is showing the electric field penetrating the current sheet. This is where the, let's see, I think I reversed the time here. So initially you can see here's the forcing, you get some electric field in the current sheet. Then this is your BZ hump as it begins to move earthward and then continues to move earthward. And when you look at the plot, so this is again cuts down the current sheet of BZ, varying in time. And what you see is without forcing, there's no increase in the amplitude of the BZ hump. But with this forcing, you do in fact get an increase in the amplitude, suggesting that this is similar ion tearing unstable as in the Harris current sheets before. And this is really leading me to this potential future direction. It's made me think a lot about what is the actual shape of the driving electric field in reality and how important is it in the magnetotail current sheet dynamics. So this is going back to the data mining reconstructions. Here I've just taken the field lines at 2 different times. Purple is later in time and green is earlier in time. And you can see close to the Earth in the dipole region, they're both dipole-like, no surprise there. But in this midtail region, you see some thinning, and further out, you see some inflating. So that's you know, you do have some DDT of B, which is, of course, is gonna give you an electric field. And you can write down this equation and solve it to get an electric field. And that's exactly what I did. And so here I'm just comparing, because of course, the data mining reconstructions are three-dimensional. But what I've done here is basically treat it like a two-dimensional problem and just thrown out that third dimension for simplicity and ease. But comparing the spatial derivatives to E to the time derivatives to B, you can see it's not that unreasonable, you know, it's not perfect, it's not a perfect match, but it should give us at least a qualitative idea of what that driving electric field should look like, at least for this particular event. And so now what I'm showing here is that driving electric field as a cut along the x-axis, that's this blue line. And then I'm showing three electric fields that are commonly used in these PIC simulations of the Magnetotail box to drive the current sheet. And you can immediately see that the one that I've been using, this green line, is wrong. It's not matching the data mining at all. This red line, also wrong, just a little differently. But this orange line is actually not that bad. It matches fairly well. The only thing I'll note here is that in my literature dive, I did not see a similar amplitude. The amplitudes used were often much larger than this. And, you know, so I think that this is an unexplored topic, and it's definitely someplace that I want to take this research to try and understand how this driving electric field might affect things. The other place I want to bring this is trying to get these thin current sheets into global models. You know, because here I am, I've been chatting your ear off about how important these thin current sheets are and why we need to study them and all that, but truthfully, I don't know what their global effect is or how important it is. And the fact that, you know, you get reconnection at approximately the same location in both thin current sheets and Harris current sheets was a surprise to me, and it's making me wonder what the global effect is. So I want to try and take these thin current sheets that we have from the empirical reconstructions and put them in MHD. So how am I going to do that? Here we have an MHD simulation of, I forget the event, but at any rate, it's an MHD simulation, and you can see a very thin current sheet here. And basically what's happening is to balance your J cross B force in a thin current sheet, you can either use the off-diagonal pressure, or you can use this basically V dot grad B term in the momentum equation. And in MHD, there's no off-diagonal pressure, but they can do it with fast flows. So in this case, we have a reconnection, we have fast flows, we can get a thin current sheet. But when you look at the empirical reconstruction for the same time, the field lines look very, very different. There is no X line here, there's just a thin current sheet. So MHD can get thin current sheets, but they're not the right thin current sheets. So I've been thinking about how to put this off diagonal pressure there, and I've written down this equation here. Basically, you have your typical MHD scalar isotropic pressure, and then you have some divergence from your thin current sheet. And this is basically that off diagonal pressure I was talking about earlier. And this is what balances your J cross B force, and you can write J as the J from the isotropic component, your MHD component, plus this thin current sheet addition. The MHD is obviously going to balance, and to get this, if we know what JTCS is, J thin current sheet is, which we do from our empirical models, then we can solve for our off diagonal pressure component, which is basically what I'm trying to do here. So we just plug in this empirical current cross B into our momentum equation, and we can put that into our global models. So this top cut here, this is just MHD, no thin current sheet. The bottom has that thin current sheet, and you can immediately see that our field lines are significantly more stretched. So this is promising, it can be done, it doesn't explode the code, those are all good things. But I want to study this to try and understand the effect of the thin current sheets a little bit more. So what I'm working on now is this Magnetotail in a box simulation. So obviously I've been studying the PIC version of this for a long time, but I've just recently started studying it in this MHD simulation. So here you can see that our thin current sheet, the currents look very similar. In both cases, the black field lines are T equals 0 and red is later on. And you can see that the red field lines are overstretching the initial field lines. They're being more stretched, which they should be in thin current sheets. And so I'm getting pretty good agreement between the PIC, which of course is fully self-consistent equilibrium, and the MHD, which is a little, lots of caveats, but still, it looks pretty good. So my next step here is to basically take this new simulation and start forcing it to get reconnection and see how it compares and contrasts with the PIC simulation. And I was hoping to have results by today, but I was unable to get there. So let's talk about conclusions. We have this new PIC equilibrium for thin current sheets. It's stable. The thin current sheet has current that overstretches the magnetic field. I don't think I made this point with the plots, but basically in Harris, your current contours and magnetic field contours overlap each other. But in this new overstretched thin current sheet, the current contours actually stretch a little bit past the magnetic field lines, and it's just a stretching effect. So we require weak ion anisotropy, which gives us some agyrotropy, and this substantially modifies the force balance. Again, about 30% of our J cross B force is balanced by this off-diagonal pressure. And the off-diagonal pressure comes from these figure-8 Spicer orbits. And that naturally explains why thin current sheets are ion scale, because they're created by these Spicer ions, and the Spicer ion orbit is inherently related to the ion Larmor radius. When we force thin current sheets, we get reconnection as expected. The surprise is that it's approximately the same location as the Harris current sheet, which makes me wonder about this driving electric field and how it can play a role in the resulting current sheet dynamics. The BZ hump instability without driving seems to be stable. There's never any reconnection in the current sheet, in the thin current sheet. Possibly due to the minimum current sheet thickness in these OTCSs, but it's a bit of a puzzle. And really the takeaway here is that our thin current sheets in general seem to be more stable than isotropic Harris current sheets, which is a bit of a surprise. I'm just going to leave that as a comment. So then I just want to acknowledge a couple of awards, the NASA Drive Center for Geospace Storms, and then we have this paper from a year and a half or so ago talking about the equilibrium, and a more recent paper talking about reconnection and forcing BZ humps and that sort of thing. And that is my talk. Thank you.
Time for questions?
Figure 8, where you were kind of, I know, I opened up. It just made me think, did you discover at all whether it is sensitive to the phase of the ions, like entering the region at all, or is it?
So which figure are you talking about?
When we showed the bunch of trajectory, a series of the trajectories, and eventually you get the figure, yeah, that one. Yeah, I was just wondering if it is more just local, if it's there, it'll eventually follow, or the phase of the orbit plays any role.
Yeah, okay, so if you think about the actual figure 8 orbits. So it's been a while since I've done this, so I'll probably do it wrong, but if you work out the figure 8, maybe it's better to look at this plot here. You can think about at what point it will contribute to the off-diagonal pressure. And I think it does matter. It tends to be. Oh.
I put you on the spot, didn't I?
Yeah,
Sorry.
I can't
No, I
remember
just
the
wanted
answer
to think.
exactly,
Yeah.
but I'm pretty sure it's opposite this, the meandering orbits. What's interesting is that these meandering orbits seem to intensify the current, but the figure 8 orbits are providing the off-diagonal pressure component. And I think that's why you get this, in the center, it's, you have no off-diagonal pressure. I think the figure 8 pushes it further away from the current sheet than these meandering orbits do. But yeah, the phase does matter a little bit. And actually, if you come back to the original Spicer ions here, I believe that the meandering ion looks like this, but it's slowly gyrating around the normal magnetic field. And when it comes back around, it starts doing the figure of 8 on the other side of its orbit. So I don't know how much that answers you. It's weird.
I just wanted a picture.
Yeah, and I think actually, so with this spicer orbit as well, once it's done a 90-degree, rotation, the particle is just either ejected or they become just exponential orbits or something, but yeah, and actually back to the figure 8 plot again too. Could you say again which, you did like an initial distribution minus the local distribution to get the red-blue base space plot there? I was kind of curious where, yeah.
Yeah,
So what were the two locations, or the two time points in time where you?
yeah, so it's, the end of the simulation, t equals 60 minus the beginning, t equals 0. So at the beginning, you have, no off-diagonal pressure component. So when you multiply it by dxvz, it's perfectly symmetric here, so that when you integrate it, it all cancels. But I was curious about, looking at basically the changes to get you that off-diagonal pressure component, which is why I took the difference.
Yeah, and yeah, exactly as you said, if it really were perfectly symmetric, even if there were like those little red-blue regions that appear, if they were symmetric, it should still cancel out, but there must be some asymmetry, like you said, if it leads to a net term. And that's actually my next thought. So when you showed some of the force balance equations, was it in the X direction you were looking at, like it was force balance in
Yes.
the X? And
Yes,
is that, so that's along the outflow?
that's
direction?
correct. Yeah,
Okay.
exactly.
And have you looked at the force balance, like say in the reconnection rate direction or like in the Y direction, or why do you choose to look more in the X direction?
Well, these are 2.5D simulations, so I have not looked at the force balance in the Y direction at all. I did look a little bit in the Z direction, but I was mostly interested in the X direction because that's the direction of the tension force of the field lines.
Okay.
Yeah.
All right, so in your, I think, first next work stuff about the electric field, you said you were using like a two-dimensional electric field, but it didn't really seem to matter, even though the reconstructions were 3D, it like mostly agreed with what you would have expected. What kind of information do you use from making it 2D instead of 3D?
Well, it's a good question, and I'm not totally sure what the answer is. I made it 2D because then you can solve the equation.
Sure.
In 3D, I'm not sure how to solve it. Maybe there's a method, but I don't know it. You're certainly gonna use, the magnetotail itself is 3D. So, and as we were talking about in the beginning, it's not symmetric in the equatorial plane. You can get weird asymmetries. So you're definitely losing that, doing it this way. But I guess I would just argue that looking at these, I'm calling them error checking plots, the consistency between the left plots and the right plots makes me think that you might be losing some, but hopefully you're not losing too much.
And that the difference that does exist between the two, like is not very impactful, like the missing electric field direction doesn't really.
Well, let me say this. Sure. The empirical reconstructions themselves, they can only do it at a 5-minute cadence. And spatially resolved, they can maybe do like an Earth radii, and they definitely can't do smaller than that. So you're already, there's only so much, even if you did it perfectly with the empirical reconstructions, it's still gonna be wrong.
Yeah.
So it's just a question of like, let's get close to right and call it a day.
So some of that may be due to the reconstruction error rather than like you'd be missing information.
Well, the error between, say, this driving electric field and the real driving electric field, right? Probably, you can't really do much better than what's already here.
All right.
That's what I would argue.
Thanks.
Just a quickie, did I understand that the thickness of these thin sheets is on the scale of the ion inertial length?
Yeah, yes, although, well, it's really on the scale of the ion Larmor radius, but that's the same as the ion inertial length in this case, so yeah.
In this, okay, because I heard you say both, so I got.
Yeah.
How do you connect something on the scale of the ion inertial length with MHD?
Yeah, that's a great question. So that's this other project that I'm trying to do over here. It's a good question. In this particular instance, which is the only time that I've tried to do this in a global MHD model, I really didn't make a special effort. The resolution of the grid here is getting towards the ion scale, I think. It just obviously it's MHD, it doesn't include any ion physics, but it's close to say, it's a fraction of an RE, I guess is what I'm trying to say. So when I take my empirical reconstruction thin current sheet, which is ion scale, I can plug it in and get an effect. But yeah, it is tricky. I guess all that I can say is that this ion scale current sheet in reality does seem to have a global effect. So I think a global effect in the sense of stretching these field lines. So I think that we should try and find a way. Another potential option is somehow trying to integrate the current in the thin current sheet and then putting that in the MHD, maybe smoothing it out a little bit, but just trying to add a little extra current. I don't know if that makes sense. I haven't done that. I've only sort of vaguely thought about it, but it's a possible solution if the thinness of the current sheet becomes an issue in MHD.
This is way outside of my comfort zone, but is there a two fluid approach you could use?
I mean, two fluid would probably help. It would change the force balance equation. I don't know, it's outside my comfort zone too, but it's possible. I mean, I think that.
Because I know they do it with laboratory places.
Yeah.
That's why I asked.
I don't know. I have to think about it. I mean, part of the problem is that from the pig simulations, it looks like gyrotrophy is an inherent part of the thin current sheet, and that the thin current sheet itself depends on these Spicer orbits and potentially the quasi-adiabatic invariant, which itself is a non-local quantity because you have to integrate over the whole orbit. So maybe you could do something with two fluids, kind of similar to what I'm doing here, where it's like you're trying to put in a thin current sheet, but it's not totally visible. I'm not sure.
Thank you.
You mentioned that the data out near lunar orbit for the reconstructions is fairly good, and I know you mentioned not having this figure available, but how does that density just off the top of your head compare in terms of data density to sort of the more inner region?
So if you look at the equatorial plane, the inner region, certainly out to like geosynchronous orbit is like super populated with satellites. Then as you go further out, it sort of becomes like, well, you have clustering of Geotail and Themis and MMS. And then there's nothing. So I think the data at lunar is probably comparable to the data at around 20 RE would be my guess, something like that, which is I think largely MMS. I think Themis goes out there.
It's Artemis that goes out there, 60 RE.
Yeah, at 60, I meant 20 RE.
Okay, 20 RE, yeah. Yeah, you've got a little more data at 20 RE, but because of Artemis, it's not orders of magnitude more.
Yeah, exactly. But it is orders of magnitude when you get inside geo. Like that's where most of your data is.
Let me just make sure I understand that concept of the BZ hump. So like looking at that top left figure up there, I'm seeing around 30 RE, looks like there's a minimum. Would that be the minimum and then tailward of that is the hump?
Yeah, this is the hump right here.
Right.
Then you can see right here, this is an X line.
Yeah.
And this is an O line.
That's
And there's, I think this is an X line as well. And interestingly, this is also a BZ hump.
Oh, okay.
Because you can see that there's a minimum in front of it.
Yeah, because it was looking like the BZ was still staying northward, but the lowest spot you can actually have southward in the next line.
Yeah, that's right.
And even if it stays positive, that's just the field's getting stretched. Is that about right?
I'm not quite sure about that last statement. Could you say it again?
Okay, even if the BZ is still northward, but at a minimum, that would just be stretched out.
Yeah,
Yeah.
there might be a distinction between stretching versus thinning.
Yeah.
I'm not gonna make that distinction, so we'll just say stretching is fine.
Yeah, I'm good with that.
Quick one, you might have mentioned this already, data mining reconstruction. In that structure, you mentioned there's a equation that handles the thicker
Mhm.
sheet and the thinner sheet. Is that for computational reasons or is there any physical motivation to?
Well, the motivation is because, is basically, you know, what I was saying at the beginning of the talk, which is that we have these thin current sheets.
Oh.
And so I think they wanted to explicitly take the thin current sheet into account because the structure of it is different from the larger, thicker current sheet, which is maybe what Harris current sheets are typically considered. But in fact, the total magnetic field is the sum of all these terms. You have an internal magnetic field, which I think is like the dipole or IGRF. You have the field aligned current magnetic fields, and you have a magnetopause boundary. And then, of course, you have the equatorial magnetic field, and that's what they split up into these this thin current sheet and thicker current sheet. And they have some, you know, crazy expansion. I think when they go out to 60 RE, there's like 1,000 terms or something. It gets out of hand.
Yes, so I was just wondering, what's the mass ratio you're using for your consideration?
Oh. I think it's 100, but I'm not positive.
Would that have any effect on the terms that you're showing, like if you used a higher mass ratio, you expect them to also?
No, because I think that, at least for the equilibrium simulation, as long as the electrons are magnetized, which I believe that they are, in the normal magnetic field, then you're in good shape. And it doesn't really matter at that point.
Wouldn't that change where they're considered to be magnetized though?
Well, yeah, but that's what I mean. If your electron mass is too large, then they won't be magnetized and then you're in trouble. But in this case, it's small enough, they're magnetized, it's not a problem. You see what I mean? Okay. And once I start doing the reconnection and the forcing, you know, as soon as you have these sorts of instabilities, then your electrons are not necessarily magnetized at the X line. They're going to be playing more an important role. And yeah, it might be worth experimenting with different mass ratios to see how much of a role that plays. I don't think we did that. But I would be surprised if it changed the conclusions. Still might be worth it. That's a good point.
Yeah, to that point as well, like when you add that extra sort of thin current sheet at the ion scale, I don't know if on the global sense it would matter if you had a third, you know, thin electron scale current sheet
Yeah,
there
right.
too, but that would be interesting to think about.
Yeah, I know that there have been efforts to talk about the, in some contexts that there might be a thinner electron scale current sheet. But I forget exactly the details now.
Thank our speaker again.